The Arctic energy budget. So the satellite platforms actually help us observe spectral radiance and allow us to calculate the energy budget. That means how much energy is being absorbed and how much energy being reflected, so that we can actually find it out. That is the spectral radiance. The spectral radiance can be measured. So from that we can actually calculate the total Arctic energy budget. So the radiative components of the top of the atmosphere and the surface energy budget and forcings can be used to calculate Arctic amplification. So there are equations people generally employ to find out how much is the Arctic amplification. See, the total Arctic energy budget is mainly dominated by the heat deficit because Arctic region is very cold. So 115.8 watt per meter squared at the top of the atmosphere on an annual average. This deficit is actually larger in January but reverts to small energy gains in July. So that means the Arctic energy means Arctic receives less solar energy in the winter and more solar energy in the summer. So that's the reason the deficit in the winters are very high than the average. It is at minus 176.9 watts per meter squared in the winter, whereas in the summertime it's actually in the positive region, that is 12.4 watts per meter square in the July month. So the reduction in mean surface albedo, that means from 0.52 to 0.48 since 1979. So what does it mean? The surface albedo reduction means the amount of ice had reduced. That is the direct inference for us. This is due to sea ice loss. That means the long-term darkening of the Arctic surface happens. So when the long-term darkening of the Arctic surface happens means more solar energy is being absorbed. So that is the observation over the period of 4 decades. So as the sea ice and the snow cover retreat, there is a decrease in the Arctic surface albedo. That means the amount of solar energy given out is less compared to more solar energy is being absorbed. So this in turn has caused the moderate changes in the radiative fluxes and forcing. So these are all the various factors which affect the Arctic energy budget. The major problem in analysis is the cloud, because when there is cloud present, it is going to, in the previous albedo effects we have seen that, and also in the solar irradiation modules we have seen that how the cloud plays a vital role in reducing the amount of solar energy reaching the earth. Similarly, the Arctic cloudiness plays a critical role in region's climate dynamics and is a key factor in the phenomenon known as Arctic amplification, where warming in the Arctic occurs at a greater rate than the global average. Understanding how cloudiness data is obtained and processed is essential for climate scientists aiming to unravel the complexities of this unique climate system. So here we look at how Arctic cloudiness data is obtained and processed. One of the primary sources of cloud data in the Arctic is a CMSAF, that is Climate Monitoring Satellite Application Facility. Cloud, albedo and the surface radiation data from AVHR, that means Advanced Very High Resolution Radiometer data, known as CLARA-A2. This dataset spans several decades, providing consistent and long-term observation of cloud properties, surface albedo and radiation. So from this we can understand how much is the cloud that is present. In fact, the CLARA-A2, that is CLARA A2 product utilizes a hierarchical decision tree thresholding method for cloud property retrieval. This approach involves multi-steps that leverage both cloud and surface characterization, allowing for accurate delineation of clouds over the diverse Arctic landscape. The second one is the NOAA's Pathfinder Atmosphere Extended Program. So this is another vital tool for monitoring Arctic cloudiness. This program employs Naive-Bayesian method to analyze satellite data and derive cloud properties. This probabilistic approach enables the extraction of cloud information even in complicated atmospheric conditions, making it especially useful in the Arctic, where variability in cloud cover can be significant. The third is the Extended Advanced Very High Resolution Radiometer Polar Pathfinder. This offers another layer of cloud observation. This dataset provides detailed information about cloud cover and properties by combining various observational datasets. It integrates both infrared and visible channel, enhancing the accuracy of cloud detection in the Arctic environment. And the last one is the ESA's Cloud CCA version 3. The European Space Agency's Cloud Climate Change Initiative, particularly its version 3 dataset, is covering from 1982 to 2017. This employs advanced techniques such as the neural network and optimal estimation. These methods enable researchers to derive cloud properties from complex satellite data, improving our understanding of cloud dynamics in the Arctic. Here is the Arctic cloudiness effect. Here we see the variations in the total cloud cover, that is image A, and a long wave cloud radiative effect on the surface, that is B, obtained from ESA's Cloud CCA and CERES data products. So here the cloud distract optical satellite surface observation and data retrieval. So this is the major problem we are having. When there is a cloud that actually distracts the optical satellite from receiving the surface data, and this cloud also plays an active and poorly understood role in forcing the amplification on all scales. So that means we do not know how much energy it blocks and how much solar radiation diffuses through the clouds. It's very difficult to predict. So in other words, it's very difficult to measure the Arctic energy budget. Similarly, that leads to complications in understanding and estimating Arctic amplification. So that there is a strong connection that has been found between the cloud cover change and dynamic patterns of the heat inflow into the Arctic. So there is a relationship, but we really do not exactly know how it is actually and how much. The quantitatively we are unable to figure it out. Currently, we only have the qualitative information that cloud affects Arctic amplification. So here is another few more points to understand this relationship. So the reduced cloudiness supports the amplification well into the autumn season when accumulated heat is released. So that means when there is no cloud, it is very easy. Directly we can relate to the Arctic amplification. We can measure the Arctic energy budget. But in the winter time, the enhanced low-level cloud fraction traps outgoing long-wave radiation. So this trapping is known as cloud optical depth feedback. So that means in the winter what happens is there is some amount of heat energy received by the surface, and that is given out in the form of long-wave radiation, and this is being captured by the cloud. So this leads complications in our understanding and our calculations. So this trapping is the most difficult one to study and measure. When the cloudiness over the areas of sea ice retreat is enhanced, this induces positive radiation forcing. That means when the ice is less, that leads to more water. When there is more water, that leads to more Arctic amplification. And the clouds reduce the surface heat loss, especially in the winter season. So they are capable of enhancing the amplification. So what happens is the energy is not dissipated, but it is retained. So that's the reason it leads to more amplification, especially in the winter month. So here is a Sankey map. The primary satellite sensor contributing to the amplification of ECVs in the ESA CCA program. So here we can see like there is a warming, and there is precipitation, ecosystem, advection, radiation, socio-economic parameters, permafrost change, and sea level. So these are all the impact factors, and these things are getting affected, and these changes are being studied by various providers, platform or instrument. So either it is a satellite or the ground based one. So we can do measurement at various places in the Arctic region, and there are climate variables which are included here: LST, atmospheric temperature, clouds, SST, that is surface temperatures, land cover, sea ice, sea moisture, and glacier ice sheets. These are all the various climate parameters which are used for the data set which is being provided by many of these instruments, and combining these two things, we can actually identify what is the changes that are happening, and that is what is given here. So this way what we can understand is like, how the warming actually takes place and what are all the factors, climate factors which are involved in that. If you look at in this one, this red line has 1, 2, 3, 4, 5, 6, 7. So 7 parameters are involved in the warming. So the first one is the LST, which is a major contributor, and also atmospheric temperature also is another major contributor. But when we look at cloud, the thickness of this red line is very small. That means this particular variable has a very little effect for the Arctic warming. And the surface temperature, it is having a major contributor, and the land cover is a very small contributor. Sea ice is a major contributor. Soil moisture is a comparatively smaller contributor. But glacier or ice sheets have no contribution towards the warming. So that way we can actually understand how each variable affects the parameters in the Arctic region. For example, when we talk about the ecosystem is being affected by all the parameters except the glaciers or ice sheets. So here the LST contributes a small amount, atmospheric temperature contributes much lesser, whereas the cloud does not contribute anything towards the ecosystem. So there is no connection here. But SST, surface temperature, is actually having some effect on the ecosystem. Similarly, land cover and the soil moisture are having some effect on ecosystem, but sea ice has no effect on the ecosystem. So this way, people had actually figured it out, what are the variables which are involved, and all these variables are measured and identified and studied using various platforms, providers or the instrument. So let us look at various factors contributing to Arctic amplification. So the Arctic amplification occurs due to local forcing and feedbacks. So it is mainly influenced. So here we have something in the green color, something in the red and something in the blue. So what does it mean? It simply means this is having a positive effect or a higher effect, and the red one is basically the negative or the lesser one. So here we call this a negative feedback. So increased carbon dioxide. So that means the Arctic amplification actually is influenced by the global increase in the carbon dioxide. So that means the carbon dioxide actually holds the long wave radiation escaping the Earth system. In other words, more and more heat is being trapped. The surface albedo variation is the second one. So here we look at the influence of absorption of solar radiation by seawater, because when the ice melts we have more water, so the water absorbs more solar energy, so that leads to Arctic amplification. So it is a positive feedback. And what about the surface warming? This is a very weak negative feedback. This is the Planck feedback. We will look at more about this feedback in our text material. Then we have vertical lapse radiation and water vapor concentration. These are having a positive feedback towards Arctic amplification. And cloud amount has a very neutral one. In other words, like the radiative flux in both visible, that is the shortwave, and the infrared bands are different. So that's the reason it's very difficult to say how much clouds actually affect the Arctic amplification. And when we look at the surface albedo feedback, this accounts to 40% of Arctic amplification. And if the surface ice melts, as we know, which leads to the formation of pond, the surface albedo decreases by 50%. And seasonal variation also plays a vital role. So these are all the factors that are contributing to Arctic amplification.